This is section 15.8, Lagrange Multipliers. I think Lagrange Multipliers are the sweetest thing in this class. They're not necessarily the most useful thing in this class, but I don't know, they just kind of feel magical when you do them, and so I'm really excited about this section. If you're not excited about this section, the point of this section is that all the optimization problems we did in the previous section, we can do them in like a slicker way that uses more algebra and less calculus in this section. So we'll actually do basically all the same problems that we did in 15.7. We'll do them again in 15.8, but this way you get to, I don't know, feel like a wizard or something. And it is more powerful, so let's see how it goes. So the way that I like to introduce Lagrange multipliers is to say that you could try to optimize a function by just guessing at the answer. So remember what we were doing. So like Lagrange multipliers are kind of like a formal way to do a really efficient guessing game. So last time we looked at the USPS rules for how to ship boxes, and we found that the length plus the girth can't exceed 108 inches. That was the restriction. And then we found critical points and used the second partials test for the objective function. But what if we just like tried to guess instead? So in the notes, there's this like crazy picture, but I don't think the picture makes much sense unless like you watch me build it. So let me build it in Desmos. So first, what's the deal here? So we were finding the volume of a box. The volume was the length times the width times the height. We noticed that like, okay, in the end, the width and the height should really be the same because they act the same in every way. So by a symmetry argument, like width and height should really be equal. And I'm calling the width and the height x here. And then the length, I'm calling it y, just so I can get Desmos to graph it. If the length is y and the width and height are both x, then the volume is v equals x squared y. And the restriction that the length plus the girth is 108 is this line, 4x plus y equals 108. So here's what you could do. You could say, well, I don't know what the best volume is, but I wonder if we can get up to 1,000 cubic inches. If you say, I want to get up to 1,000 cubic inches, you get 1,000 equals x squared y, which is this graph, this blue graph. And you can find that, like, sure, you can get 1,000 cubic inches if you do one of these measurements, like 26 by 1.4 by 1.4, or 3... Wait. No, the x is the width and height. So it would be like 26 by 26 by 1. So you could have like a really big pizza box. Or you could have 3 by 3 by 95. That would be like a really long roll of wrapping paper or something. It's more like a lance. It's like 3 by 3 by like 8 feet. So you could ship a lance in USPS, or you could ship a huge pizza in USPS. But we can probably do better. Like, could V be 2,000? Oh, it won't do that. Okay, right. Desmos, if you want two options for something, you put them in brackets. Could V be 2,000? When V is 2,000, you get some other solutions that work right here. But wait, maybe V could be 3,000. And this guessing gives you level curves of z equals x squared y. We are looking at x squared y equals 1,000, x squared y equals 2,000, x squared y equals 3,000, and we can keep going. Now we have inside knowledge from doing the problem before that we know the maximum volume is this 18 by 18 by 36, which is a volume of 11,600. But if you were just guessing over and over, let's do like 2,000, 4,000, 6,000, 8,000, 10,000, 12,000. If you're just guessing, you'd be like, okay, well, it seems like we're really zeroing in on the answer here. This curve is all of the boxes that have 10,000 cubic inches of volume. And this one is all the boxes that have 12,000 cubic inches of volume. The 12,000 cubic inches boxes don't work. They're outside of the required dimensions. So the maximum must be like somewhere in between 10,000 and 12,000. So you might say, okay, well, I'll go look at these level curves, 10,000, 10,500, 11,000, 11,500, 12,000. I'd be like, oh man, it looks like we're really getting there. It looks like it's something like 11.5. And in the perfect situation where v was the perfect exact number, like the actual maximum. Wait, what was it? 11. You should imagine, though, that by looking at this picture, you could come at this number and get it by trial and error, actually, that it was 11,664. That this point here, where I got my restriction, the restriction on the box that was from the rules of the Postal Service, and the level curve of my objective function to just barely touch. At that point, that's the highest that we could possibly get for my objective function. Let's see if I can finish up recreating that picture. Let's do like 3664, 5664, ... and then like 15564. So we've got our restriction and the level curves of our objective function. And the maximum value of the objective function happens when the level curves are tangent to the restriction. That idea, if we could write down an equation that would say the level curve of the objective function is tangent to the restriction, that's the maximum. It's also where the minimum happens, but there is no like good minimum for this box. Okay, so let's try to actually write that down as an equation. What is surprisingly true? Yeah, so the maximum volume is at this place where the level curve of objective is tangent to the restriction. Okay, so we're going to try to write this down as an equation. Like that implies that there's an equation to be written. How do you tell that two curves are tangent to each other? You need them to be headed in the same direction. For two things to be headed in the same direction, they need tangent vectors that are going in the same direction. So what we'll do is we'll try to say that the direction that the level curves of the objective function go are the same direction as the restriction. So let's do it. So to optimize an objective function, we're calling the objective function f. Here it is. We look at the level curves, and we want the level curves to be tangent to the restriction, which here, this is a better name for it, I'm sorry. It's called the constraint function. The constraint was the rule put in by the USPS. In the real world, you'll have all kinds of different constraints, but there'll be something that stops you from just making $1 billion or shipping a whole house through the Postal Service. That's the constraint. To make them go the same direction, you say that you want their gradients to go the same way. So you want their gradient vectors to be parallel. And how do you write that? You say, okay, to have two vectors be parallel, you need one to be a multiple of the other. That's this. So to have the level curves and the constraint function be tangent, you make their gradients be parallel, which means you make their gradients be a multiple of each other. The multiple, I don't really care what multiple it is. Like if the level curve is zooming by and the constraint function is going slow, I would maybe have like a really big multiple. I don't care what the multiple is as long as it's a number, as long as it's a scalar. So we use this lowercase lambda. This is lambda, this is a lowercase Greek L. It's L for Lagrange, which is who this is named after. So we do the gradient of f is a multiple of the gradient of g. F is our objective function, g is our constraint function. So to solve a problem by Lagrange multipliers, you just set these equal, and then this thing is the constraint. The logic is sound. Like we saw it happen by some kind of guessing game. You can go back and rewind and watch it again if you want, but like the maximum happens where the level curves are the same way as the constraint function, and these equations just make that happen. So this is awesome. Let's solve the problem by this new slick way. So the main thing is you need an objective function. And you need a constraint function. And in Lagrange multipliers, they're called f and g. And the two things that you're going to try to do are you're going to try to make the gradient of f be a multiple of the gradient of g. And you're also going to actually write down the constraint. Okay, so we've got given a rectangular box where the width and height are equal. Oh, really? Where the width and height are equal? We can do such harder problems than this. Oh well. Okay, given a rectangular box where the width and height are equal, what are the dimensions of the box? Well, the objective function is the volume, because we're trying to find the maximum volume. If the width and height are equal, then we can call that, did we call it x or y in my Desmos graph? X. So we'll say that the width and height are equal x, and we'll make the length be L. So we'll have the volume. This is so confusing with all these letters. I'm going to write that the volume is length times width times height, but width and height are equal, and we'll make those both be x, so this will be x squared. The length, whatever, we could call it y because that's what we had previously, but I don't want you to feel like it's always x and y, so let's just make it L. L is confusing because we have a lambda. Okay, fine, whatever. We'll use x and y. And then because this is the objective function, I'll call it f. The constraint is that the length plus all the way around, so the length plus the girth, is 108. This is g. So g is y plus 4x. So what do Lagrange multipliers do? They tell you to take the gradient of f and set it equal to a multiple of the gradient of g. So you find gradient f. This is a function of two variables, x and y. So the gradient is a vector that has an x and a y component. It's got the x partial derivative in the x slot and the y partial derivative in the y slot. Same deal for the gradient of g. This is the gradient of those level curves. And this is the gradient of the constraint function. If those are pointing in the same direction, then we're good. So that will be that 2xy x squared is a multiple of 4, 1. How can we write this as like equations that we can actually solve? Well, if you have two vectors equal to each other, then their components are equal. So we get, so here's gradient of f is a multiple of gradient of g. We can write it as two facts. One about the x component, 2xy over here equals 4 lambda over here. And x squared on the left equals lambda on the right. The Lagrange multiplier system is gradient f equals lambda gradient g, and also that g equals some constraint. And this is, you just write the constraint function. Or, not the constraint function. You write the constraint equation. This is a system of 3 variables with 3 equations, so we should be able to solve for x, y, and lambda. The trick here is you don't care about lambda. So, I mean, you can solve for lambda, but what we really care about is the variables. Here it would be x and y. So why it matters that we don't care what lambda is that lambda is a good, it's a good candidate for substitution. Because if we solve for lambda and substitute it into the other equations, then like lambda will be eliminated from our system. So let's be careful here. I'm going to solve for lambda in the second equation and substitute it into the other equations. So instead of 3 equations, I'll now be down to 2 equations, and instead of 3 variables, I'll be down to 2 variables. When I plug lambda into the first equation, I get 2xy equals 4x squared. When I plug lambda into the third equation, nothing happens. But it's important every time you do substitution that you keep track of how many equations you started with and how many equations you have now, because you need to go down by one equation and down by one variable each time. Otherwise you'll get lost. There will just be a sea of equations everywhere. When you're solving a system of two variables, it's not hard. Like, as soon as you do the substitution once, you've got one equation with one variable. But here it's a little bit trickier on the algebra side. So we eliminated lambda. Now we're down to just x and y. Now do it again. Solve for a variable and substitute it into the other equation. So here it'll be y is 108 minus 4x. And I can substitute that into the first equation. And I'll get 2x 108 minus 4x is 4x squared. And this will tell me this is now one equation just in x. So I can solve it for x. Let's multiply it out. 216x minus 8x squared is 4x squared. I can get all the x's. I guess I'll collect everything on one side. So I'll have 216x minus 12x squared equals 0. Factor out an x. That means I'll either have x is 0, that's not likely to be our best box, or 216 is 12x, and this is going to be our good box. Divide both sides by 12. I think 12 times 16 is 216? Or is it 12 times 18? No, it's 12 times 18. So x is 18. What's our final answer? We want the dimensions of the box. Here's the width and height. So it's going to be something by 18 by 18. Y equals 108 minus 4x tells us the other dimension. 4 times 18 is 72. So y is 36. Of course, it's the same answer as when we did it in the previous section, because it's the same question, so it should have the same answer. But the method is completely different. Instead of doing a whole bunch of calculus with first derivatives and second derivatives and some weird discriminant that has some logic that's based on which way everything is curved, instead we're thinking about everything in terms of level curves and making the level curves be tangent to the constraint function. That means we end up doing harder algebra, but way easier calculus. That means this way is almost always better. It's definitely always cooler, because the answer just appeared out of nowhere. So I really like this method. The problem is that it requires you to be really good at the details of these data types. Wait, what is gradient of f? What kind of thing is that? What's gradient of g? What kind of object is that? How could they be equal? What does that mean? Well, you get two equations. Yeah. The other nice thing about this method is it works for any number of variables. So it's really awesome. I don't know if I've convinced you. I guess it's not one of the objectives of the section to convince you that the section is awesome. This is really cool. Okay, let's do the other problem. The other problem was we had a box, and the box's restriction was that it had a vertex at 0, 0, 0, and a vertex on the plane. Sorry, we're not in a computer lab. So we had 0, 0, 0, and there was a plane over here, and you get to pick any point over here on the plane, call it XYZ. And when you pick that point, that determines what box. That's the opposite corner of the box. Then the question is to try to maximize the volume of the box. So what is the volume of the box? The volume of the box is x times y times z. That's our objective function. The constraint, so this is going to be f. The constraint is that x plus 2y plus 5z equals 10. So the constraint function is g equals the stuff that's in the constraint, x plus 2y plus 5z. Notice that x plus 2y plus 5z equals 10 is not a function. That's an equation. So the constraint function is just the part that equals some number. It's a little bit tricky, but yeah. Okay, so this is the constraint function. Then how do Lagrange multipliers work? Well, you need the gradient of f to be a multiple of the gradient of g. So let's find the gradient of f. The gradient of f will have the x partial derivative, the y partial derivative, and the z partial derivative. The gradient of g does the same thing, but here the derivatives are a little easier. The x partial derivative is 1, the y partial derivative is 2, z partial derivative is 5. To make the gradient of f be a multiple of the gradient of g, I need each of these components to be lambda times their corresponding component. So the final system that we'll solve is going to be mostly made up of facts from this. And then there's also going to be the one fact at the end where g equals the actual constraint value. So the actual constraint value was that x plus 2y plus 5z was 10. But these other facts that have something to do with, now it's level surfaces and the constraint surface, yeah, but it's awesome, is that the parts from gradient of f have to be the lambda times their corresponding part in gradient of g. So you just write all those down. This one is xz is lambda times 2. This one is xy is lambda times 5. Yeah, that's fine. This gives us 4 equations with 4 variables. So we can use elimination 3 times. Elimination? No, we can use substitution 3 times to go from 4 equations down to 3 equations, down to 2 equations, down to 1 equation, and finally get the final answer. The point here is that the calculus part of this problem is done now. There's no second derivatives, there's no mixed partial derivatives and weird discriminants. The cost is the algebra, but if you're organized, then the algebra is so much easier. So the first variable I think you should substitute is lambda. So I'll substitute lambda into all the other equations. So I'll get xz. How can we denote this? I guess I should say like what I'm doing. Let's say that I'm using lambda equals yz. So the second equation turns into xz equals 2yz. The third equation is now xy is 5yz. And the last equation is still the same. The value of writing them all is that you can see the substitution step and exactly what it did. It turned 4 equations with 4 variables into 3 equations with 3 variables. And if you can stay that organized, that each substitution step takes you like 1 step closer to the answer, then you won't have equations everywhere. Equations everywhere is like usually what happens, and I hope it does not. Some of these have common factors. I know that my true final answer is not going to have z equals 0 as the final answer, so I can divide both sides by z. So I'll have x is 2y. And for the second equation, I can divide both sides by y. That's x is 5z. And the third equation, I don't see any easy way to simplify it. I still have 3 equations and 3 variables. Now I can do a substitution. And it's important to be like somewhat organized with this. Like don't take stuff and substitute it all randomly all into each other. Like you want to solve for something in one equation and substitute it into all the others. So I'll use that x is 2y, and I'll substitute x equals 2y into the other 2 equations. That gives me 2y equals 5z, and x is 2y, so 2y plus 5z equals 10. It seems like laborious, but it's worth it to be organized. I'm now 2 equations with 2 variables. Finally, for the last substitution, I can just substitute that 5z, that like 2y is 5z. So I'll change these 2y's into 5z's. Now I went from 4 equations, 4 variables, to 3 equations, 3 variables, did some manipulation to make my life easier. 2 equations, 2 variables, 1 equation, 1 variable. That I can solve. This is 15z equals 10. Z is 2/3. Then, because I used substitution, each step of the ladder to get back what y and x are all set up for me, and they're right here. This says 2y is 5z, and that's going to tell me what y is. So 2y is 5z, means y is 5/3. And then x is 2y, means that x is 10/3. Technically, we could find lambda. Lambda is yz. But lambda is this weird thing where, like, we could solve for it and we don't because we don't care. As long as you do the substitution correctly, you'll never actually have to find it. It's not wrong to find it. It's just like it tells you like the multiplier that gets between the normal vector of the level surface and the normal, like it doesn't mean anything for the optimization problem. The lambda is just our way to tell that these things are tangent to each other. So I don't actually end up solving for lambda. In the end, what's the question? Maximize the volume. I think maybe we just want to find the maximum volume. I don't know, the question is unclear here, so let's just answer it both ways. So the box should be 10/3 by 5/3 by 2/3. And the volume is 100 over 27. If you look back at how this problem was done in section 15.7, there were a lot of derivatives and a lot of second derivatives. And it's like, I don't know, it's a lot of calculus. And generally we try to build our calculus methods so that they're like as nifty as possible by avoiding calculus as much as possible. In this case, I don't know, you may be thinking when you look at this like, oh my gosh, let's do this every time. But once you get into the practice problems, you'll see that it's really hard to be disciplined enough to solve the systems really quickly. So practice them, solve some systems, start by eliminating lambda whenever you can. This trick that I did where I found some equations and I didn't like them because they were too complicated and I made them easier, use that trick whenever you can. And Lagrange multipliers are awesome, and you should just use them whenever you have an optimization problem. Okay, I think we have one more thing. Yeah, so this is cool. So this says, let's try to find a triangle where the sum of the sines of its angles is as large as possible. The sines of its angles. Okay, well, because I know Lagrange multipliers, I'm like just not that worried about this. I'm going to, this is the thing I'm trying to maximize. So that's my objective function. Here's some triangle. It's got, let's say, alpha, beta, and gamma as its angles. And the thing we're trying to optimize is sine alpha plus sine beta plus sine gamma. Well, what's the restriction? Like, what stops us from making like all crazy numbers here? The restriction is that the angles add up to 180 degrees. They add up to pi. Now, what part of this is the objective function? This part is the objective function. G is alpha plus beta plus gamma. That's the objective function. Oh, this says to do it both ways. Oh, hard pass. I'm doing it with Lagrange multipliers. So let's do it. Is this good? I think this is good. Okay, so we're going to need the gradient of the objective function. That means we'll have to take the alpha partial derivative, the beta partial derivative, and the gamma partial derivative, and put them in a vector. Then we'll similarly have to find the gradient of the constraint function, which here is the alpha partial derivative, the beta partial derivative, and the gamma partial derivative. Then we set up the system for Lagrange multipliers. Most of the system is that the gradient of our objective is a multiple of the gradient of our constraint. Here again, it's going to be three variables, or three equations. It's that cosine alpha is lambda times 1. Cosine beta is lambda times 1. And cosine gamma is lambda times 1. So all of these angles, they have the same cosine. This is most of the setup. Then the rest of the system is the actual like g equals some number. And here that's alpha plus beta plus gamma is pi. So in total, I end up with 4 equations with 4 variables. If you have a bunch of angles that all have the same cosine, aren't they the same angle? I guess if they're inside a triangle, they are. So this says, like you can have 2 angles with the same cosine that aren't the same angle, but they have to be, like one of them would have to be negative or bigger than pi, and that's not possible. So since all of these are between 0 and pi, all this tells you is that they're all the same angle. And if you combine that with the fact that the angles add up to pi, then that means that they're all pi over 3. Oops. So the question says, describe the triangle for which the sum of the sines of the angles is maximum. It's an equilateral triangle, which I just spelled with a W for some reason. So it's an equilateral triangle, and that sum is, well, let's plug it in. Sine pi over 3 plus sine pi over 3 plus sine pi over 3. What is the sine of pi over 3? I guess it's root 3 over 2. So it's 3 root 3 over 2. So the equilateral triangle has the biggest possible sum of sines of its angles, and that sum is 3 root 3 over 2. It's just awesome. I don't know. Like, I don't know if you believe, like, I barely had to think about the geometry of the problem to do this because of Lagrange multipliers. So essentially, anytime you have an issue in science or engineering or economics or whatever, and you need to maximize something, which is basically all the time, you should figure out what your objective is and what your constraint is. The constraint will have like a function equals a number usually, and in that case, the function part is called g in this process. The objective will be a function, like you won't know what it equals, so that will already be a function. You take the gradients of both, you set one of the gradients equal to lambda times the other, and that builds you most of a system. Then the rest of the system is just the actual constraint, the constraint equation. If you solve that system, you did it. You get the maxes and mins. Awesome. You need to practice this though. I make the systems look easy because I've done a million of them. Practice the systems, practice being organized in how you solve the systems, going from 4 variables to 3 to 2 to 1. It's just really powerful.